reflections on rooms, and I will try to be fast because I cannot cover all of the details, but basically the objective is to characterize the quality of the reflections and make better designs for studio or home theaters or whatever small spaces is tackling. We have as a background, we have 3 types of microphones that can be used for mapping in 3-dimensional the reflections, and I'm just using the coincident array. I'm just covering this as general technology. There's a technique called beamforming, and this is the type of arrays that are used for that. It can be a little ambiguous when you have a reflection that come on both sides, like that cannot be localized properly. This is the coincident array. Basically, this type of microphones can imagine a point in the center of the array that has the properties of the vectors in azimuthal and elevation and magnitude of the intensity of the sound. And the more advanced the techniques are using the intensity probes, and basically the most advanced one is using the particle velocity vector. That's the one that we have on the left. It's called a microflown probe, and potentially is the future because it's measuring particle velocity instead of estimation of particle velocity with pressure microphones. The one that we have on the right is made by Grass, and it's less accurate than the one that has on the left. Coming back to the sound field microphone that I am using, these are the equations that are used for calculation of the A format. A format is the when we measure, the signal is coming in 4 channels, and it's called the A format. Then A format is the raw data. Then it's by some matrix manipulations is transformed to orthogonal virtual figures of 8 and pressure signal. And from there I am using it for analyzing the input response of the room. That is basically the transfer function, the frequency response that can have all the peaks on the frequency. And this technique is done with a software called WinMLS, and the new technique is that we are doing it in 3 dimensions with 4 signals. So we have the pressure signal, X, Y, and Z signals as time series decaying signals. And well, this is the A format pattern in 3 dimensions. We have the sum of them creates like a tetrahedral array in 3 dimensions. But from the D format, we have orthogonal components in X, Y, and Z, and that creates all the needs for making a vector with all the components. The only difference that we have is that these signals needs to be corrected in gain, so that's why I am dividing by 1/√2 all the signals, in order that, as you see, all the gains correspond to the same value. Okay? So with the orthogonal components, we can calculate the intensity in 3 dimensions, and we also can calculate a figure called diffuseness estimate. This figure is basically it's a measure to estimate how random is the incoming reflections in all the directions. If the sound is very specular, I mean, when it's bouncing from a wall, it will capture most of the signals in one direction. and that's giving a very low estimate on diffuseness as 0. Okay, so this is the technique that I am using now for estimation of intensity. It's based on spectrogram short Fourier transforms, and basically is that as you maybe have seen before, it's the time series is discretized in subindex n, and then it's multiplied by a shape window called hand window that basically is improving the response to frequency, because if you don't multiply by a window, you can smear all the harmonics in a bad way, and the estimation of the intensity will be underestimated. And well, once everything is already multiplied, you just convert it to the frequency domain by applying the fast Fourier transform, and from there I will show fast what are the equations to do it. But basically we have an estimation of the three-dimensional intensity vector. Then we calculate estimation of the absolute value with the norm of the vector, and then we divide that between the estimation of the energy density, that is the sum of the kinetic energy and the potential energy of the particles that are vibrating. And from there, you have angles in horizontal, vertical, and the diffuse estimate. After having that, it's important to resemble how we hear, and we measure our ear. It acts like a bank of filters, like a Fourier, like a bank of filters that is called the equivalent rectangular bands. Basically, we have a less resolution on high frequencies because our basilar membrane in the inner ear, in the cochlea, has a less resolution on high frequencies, but will be explained in the next slides. So, well, this is the multiplication of the signals X, Y, and Z, and the pressure signal by the hand window. We calculate the real part of the intensity. If we make an extrapolation, it's like using the real part of the power factor in electrical circuits. So we just want the net flow of energy, not the reactive part that is not giving us any estimate. And well, the parameters that we're dividing are the acoustic impedance of the air, and the root of 2, it's just to scale factor the parameters. So, well, we can create the intensity vector in 2 subindex, n in time and k in frequency, and from there we just do the typical equations for acquiring magnitude and direction of vectors. It's important to note that the intensity is negative signs in everywhere, because if we don't reverse the sign, we will have the vector pointing opposite to where we want to localize the reflection. After that, this equation that is quite big is what we call the diffuseness estimate. This is the work of an author called Juha Merima from 2004, and basically it's applied in small rooms with higher resolution than it was done before. It was originally done for Hall recording, big spaces that has bigger reflections and density in time, and when we apply to control rooms, it's quite the opposite. We have very short reverberation times. That means that the sound decay very sharp and very fast. So from there, the equivalent rectangular bands that basically average the signal in frequency domain between the different bands, and the model is very simple. It's like a linear increment model that creates bigger and bigger and bigger equivalent rectangular bands if the frequency is increased. And well, the important thing, my measures. The case of the study was measure a small control room from the music department. well, not the music department, the music tech building, and this is the photo of the place. We estimate the reverberation time, and from there the mean free path. The mean free path is the mean time that the sound will be bouncing between each reflection. So from that value we can estimate a time window for our analysis on short wave transform. That mean free path value proved to be too big for detection of reflections. It was around 6 milliseconds length on each window that will be all overlapped by the half of its length. But at the end I end up using 1 millisecond, and that proved to be more exciting for localization of reflection. So this is the room. I'm just rotating now to show the results. So our front will be 0, and I tested with two speakers. One was located at, for instance, my microphone here at the back left rear. So that means that the speaker was up here and the source was here. Well, this graph shows, the upper graph shows the intensity level. It's a mean estimation between each band in frequency. So we have many equivalent rectangular bands, and I chopped the signal up to 10 kilohertz due to the loss of resolution at high frequencies with the B format microphone. It's showing the coherency between the first direct sound, but we have a problem with high frequencies. The direction is a little biased because of the figures of 8 that creates are not accurate enough at high frequencies. Then we have some random reflections up to, we find some coherent reflections here. This may be one ceiling or floor reflection, and usually when you don't have the complete frequency here, it means that the sound was absorbed in some way, and only a specular reflection is found from, for instance, a table or something that just rebounds the sound on high frequencies. This one is a little more obvious that it's a wall, one of the walls. And what we can see is that the next couple of milliseconds is completely random again. We cannot determine too much, but that the sound is becoming diffused in a fast pace. This is another measurement made with the speaker at the front, and we can see that there's some smearing of the frequency with that time window, so we can still make it shorter and define a better resolution. The same, we have here the back wall and some possibly reflections that come from the ceiling or the floor. Okay, so that's basically the results explained. No, sorry, I haven't explained this area. This is the diffuseness estimate. If it's whitish,